अच्छा, स्क्रीन आपको नजर आ रही है? Can you confirm that you can see the screen?
यस सर, नजर आ रही है।
अच्छा. So today we continue with these practice problems. But sometimes you need to, although this in this course I told you quite a few times that we will not be solving differential equations, but sometimes there is a question which you can answer without solving the differential equation for simple harmonic motion, because this simple harmonic motion is you experience this over and over, so we need a quick way of guessing its solution without solving it. So you have seen this. Any simple harmonic motion must be a solution of a differential equation of this form. You have double derivative, the minus sign, and the omega n squared is the natural frequency. So instead of solving it directly, if I take this minus, so this is now a method of developing some intuition. Okay, so I'm taking this omega n squared with the minus sign to the other side. So you see it comes to the other side, derivative, double derivative as it is, and on this side I'm only left with x. But what I tried in the middle is that I can see this double derivative as if I'm applying that double derivative twice. I apply it once and then I apply it twice, and that minus sign, for simplicity, I keep it inside the bracket. Okay, I can keep it outside as well, but this will simplify the math later on. One more thing you need is that instead of just differentiating with respect to time only, because this omega n is also squared, so you can also differentiate with respect to this time, which is not the actual time, but it is the normalized time, omega n times t. Yeah. So you remember t is time and omega n is frequency, angular frequency. When you multiply the two, you don't have any units. So omega nt differentiate with respect to omega nt and then with respect to omega nt again. So you start with x, differentiate with respect to omega nt, put the minus sign, and then you differentiate again, and the effect of doing this twice with the minus sign once is the same as if you do nothing to x. Okay. Now this is something which you can do without any intellectual effort required. But what I am doing next is not something you have done in the course of differential equation. This is a new way of looking at things. So this is a new way of looking at things. So and the motivation comes basically from this. If I label whatever I have in the bracket, let me just label this as y for simplicity. So that thing gives me an equation. So this first equation is just a definition. Yeah, I'm just giving it a new label. The only difference between this is that I put the minus sign there. Okay, so it's the same thing. So, and once I define y in this way, then I can differentiate that y. Yeah, so I know that if this is y, derivative with respect of y with respect to that thing is x. Yeah, so derivative of y with respect to that thing is x. So I have reduced this differential equation into a set of two first order differential equations, the first one, the second one. Now you might say, okay, what do we gain from this? You will now gain a lot of things, because you can now visualize these two differential equations in a plane. How? So if you label x here and if you label y on the y-axis, I can now combine these two equations into a single equation in the complex plane. You view this as the complex plane. Okay. So this x and this y, so this is x, this is y. I differentiate the pair of these two variables. Yeah, and that's why I can imagine a complex plane. And if I take the pair of these two, and if I look at this, it turns out that this pair and this pair differ by a rotation of 90 degrees. So I can imagine that the effect of applying this derivative operator is the same as applying J only. J is, the rotation operator, yeah, the 90-degree rotation operator. So this is now the highlight of all this discussion. As far as the pair XY is concerned, you apply d over d omega nt, or you apply J, it's the same thing. So the effect of differentiation is the same as rotation. So I can literally say that the derivative is equal to this j omega n as far as this pair is concerned. Of course, this cannot be true for every situation, but because we are dealing with simple harmonic motions, you should not generalize this to any other equation. As far as simple harmonic motion is concerned, we derived this rule from this equation, so this must be true for any simple harmonic motion. Now, the advantage of having a single differential equation is that you can solve it. Yeah, you know how to solve this. So you assume some initial conditions, you put that initial condition in some polar form, either in this polar form or in this polar form. There are different ways of converting a rectangular form into a polar form. You see here the theta is with respect to x-axis, here phi is with respect to y-axis, and this you can check at home. But the ultimate conclusion from all this algebra, which you can repeat at home, is that you can easily recover the solutions from this using Euler identity. Okay, Euler identity. And not only that, you can differentiate the solution and see the expression. You differentiate again, you see the expression, and so on. But what you can see now, although you can carry out this differentiation yourself as well, but I don't want you to do that. Okay, what I want you to do is to notice this thing. Differentiation with respect to time is the same as multiplication by omega n and then changing the phase by plus 90 degrees. That's what we are doing here. We start with this solution, we differentiate with respect to time, and that is the same as multiplication by omega n, and changing the phase by plus 90. Whether you use this form or this form, in both cases the result is the same. Multiply by omega n, change the phase by plus 90 degrees. You differentiate twice, so you apply this operation twice, which means j will be twice and omega n squared will be twice. Omega n squared, and j squared means that you add that 90 degree twice, so plus pi, and that is why you get this minus sign. Okay, so if you can remember this thing, this will save you a lot of time. You won't have to actually solve equations. One immediate consequence of these relationships is that if you know the amplitude of, for example, x, the amplitude of x dot is simply that amplitude multiplied by omega n, and you know the difference in phase. Similarly, the amplitude of acceleration is omega n squared, and this difference of phase can be seen here in this plot as well. Okay, this is something you have seen in circuits as well. So if this is x, let's say it starts with 1 at time 0, it can start with any value. So the first derivative lags by an angle. Actually, it doesn't lag, it leads. Okay, because d by dt is the forward differential operator, so it leads. And similarly, the other one leads too. So this is something we will utilize in some problems. Although you should not take this derivation so seriously, it was only for those of you who can follow this discussion. I do not expect you to actually reproduce this derivation. You only are expected to deal with either of these two forms, either this form, which is typically used in the book, or this form. You are free to choose whichever of these two forms. it doesn't matter which one you choose because ultimately you have to put the initial conditions, and it's the initial conditions which will dictate these angles. Now let's start with a problem. And remember, this was actually a side note, but our last lecture was concluded with the observation that our input can not only be force or torque, sorry, but the input can also be displacement in this case. And you don't care where that displacement is coming from. You definitely need some cam drive mechanism, or your input can even be an angular displacement, theta, for example. So this example is based on that observation that we have a situation where you have a rolling, a cylinder rolling, and of course you want to track its displacement, its own displacement and its own angle, mass, radius are given, but it is connected to a spring, and that spring is stretched by some time varying displacement. It should be seen as a signal. A signal is just a time dependent quantity. Okay, so x of t will basically depend on y of t, and that y of t is to be seen as an input. Now because we are not going to solve the differential equation, so I'm going to ignore part B here. That is not the focus of this course. In part A, we are only going to write the equation of motion in terms of x and y. So our differential equation must have x and y in it. Okay. Now do not confuse this y with the y we had in this slide, because that was our own artificial definition. This y is a displacement given as an input. Okay. So the first thing we need to do, and we have been dealing with these problems. The only difference is that we have a spring now. Okay, so apart from the spring, we know that if it rolls without slipping, we know that the friction force, okay, the friction force, you can assume a direction for the friction tangential force Ft, and you remember that Ft must not be equal to the maximum friction, otherwise you will have slipping. For slipping, this Ft must be less than the maximum value, but we don't care about that maximum value. Okay, so now we have the free body diagram, which is on which you have one force applied on the left. Okay, maybe for the free body diagram we can imagine that force to be applied like this. Yeah, you can choose your free body diagram to be like that, and depending on what you assume for y and x, since you don't know the value of y and x, you can either assume x greater than y, or you can assume x less than y. In both cases you will see different results. So let's say I assume x greater than y. If I assume that, and if I take y as my reference, then greater than y means that I am trying to push the spring to the right with respect to y, with respect to this end, if I assume that to be stationary. The left side will move relative to the right side in this direction, and that means that the restoring force will be in this direction. So my restoring force will be in this direction, which is k x minus y. Remember, I am assuming x to be greater than y. Okay, or let me change this now just to make sure that you know what I'm the reasoning. Let's say I assume x to be less than y. Okay, when x is less than y, then what you assume is that if you again take that as your reference, it is the same as if this end is moving to the left relative to that y, okay, to that end. So in that case, your force will be k times y minus x, but it will be in this direction because you will be stretching the spring towards the left, and this will be the restoring force. So now the free body diagram is clear, and that is and maybe we should show this free body diagram here so that we also use it for the moments. So we will now write the force equations, Newton law, force equation, and because there is moment involved about the center, so we will also have to write the moment equation. Yeah, in the first lecture I forgot to actually write this moment equation, and that's why the solution in that lecture was incomplete. So we will now write the complete solution. So the force equation is simply Newton's law. So m times x double dot. Remember, this x and y both were needed only to write down the expression for the restoring force. Once you want to write the equation of motion for the rigid body, you know that the variable of concern is only x, not x minus y or y minus x. Okay, that's for the spring only. So mx double dot is one force is ft, the tangential force, and it's against the direction of x, so it's with a minus sign. And this k times y minus x is in the same direction, so it's with a plus sign. And similarly, we can write the if this is theta, so I can write theta double dot, yeah, and I can write the moment of inertia I, and here the only unbalanced moment is ft times r. Okay, and remember, theta is in this direction. You don't care whether it's clockwise or anti-clockwise. The moment of this ft is in that direction, so that's why it's a plus. Okay, you don't care about the convention here. And you can also remember that I for a cylinder about its center is half mr squared. That is something you already know. So I can now cancel this r with one of these r's. And one more thing which I can do is that because I want in my equations only x and y, so I'm not supposed to have theta. So now roles without slipping will now help me. Roles without slipping means that x equals r theta. So x dot equals r theta dot, and x double dot theta equals r theta double dot. So theta double dot is x dot double dot over r. So which means that I can now replace this theta double dot by x double dot over r. Okay, and actually I got rid of r. I don't know if this is if we have made any mistake. So let me just try this again. It's half m r squared, and this is ft times r, and theta double dot, and theta double dot is x double dot divided by r, this r and that r. Yeah, so this is the thing. This is correct. You don't need r basically, although the value is given. Okay, so now you can basically add these equations because I want to get rid of this unknown force Ft. So the minus and the plus will cancel out, and I'm left with the on the right hand side I'll have ky minus x, and on the left hand side I have x double dot, and m plus half m is 3 halves, yeah, 3m over 2. So if I take this 3 over 2 to the other side, this will become 2/3, and I can take this m to the other side. It will be 2k over 3m, and you see this is my angular velocity now. Yeah, the square of omega n, because this minus x. Now you see this y because that's an input. Now normally you don't have an input, So if you now it is in this form that minus omega n squared x minus y, if I take that minus sign out. इसमें कोई question है? Because we have been dealing with these equations over and over. The only difference here was the spring, and we only needed to include that forcing function, that restoring force. Other than that, this is pretty much what you have been doing so far. And I'm skipping this solution part, okay? Because we don't want to bother ourselves with solution of differential equation. Let's move on to the next example. And in this example, you have two rigid bodies, two springs, and when you have two rigid bodies, you definitely will have two displacement variables. And don't forget that this symbol represents the equilibrium in this case, and this symbol represents the support in this case. So here we basically, although it's a vertical spring, and we do have some effect from gravity, yeah, M1G, M2G, but you know that all those gravitational effects, if you take these to be your equilibrium points, the gravitational effects, they simply cancel out, okay? We have seen this over and over. So we will not write down, we will assume that the gravitational effects of M1G and M2G, they cancel out in the static deflection. You remember? You will have static deflection here, and we simply cancel those out with the gravitational forces. So now the next question that comes is the restoring force. Restoring force ऐसे होगा या ऐसे होगा, उसका ताल्लुक है by what you assume about x1 and x2. So if you assume that x1 is greater than x2, then you have this diagram. कैसे? If x1 is greater than x2, relative to x2, you are stretching k1 down. So that will be opposed by a restoring force there. Okay? And the effect on the other side will be opposite, action reaction pair. Okay? Okay. Similarly, if this is your reference and if x2 is positive, which you assume in this case, then you are essentially stretching k2 downwards, so the restoring force will be upward. That is the situation when you assume the inequality in this way. If you assume the inequality in this way, because you don't know x1 and x2, so you can also say x1 is less than x2, then these two arrows won't change because they are not related to the relative magnitude, but these two arrows will change. This will reverse, okay? These arrows will reverse. The expression will also change with the minus sign, and that's why you see the arrow reversal. Now, it doesn't matter whether you use this convention or this convention, both of them are equally good for writing down your differential equations. So let me just choose this one and write the force equations. There is no rotation here, so we don't need a moment equation. So let me write down the force equation for M1. So M1 x1 double dot. I'm ignoring the effects of gravity. And similarly, M2 x2 double dot. M1 experiences this force, F, and because this force and the x1 are in line, so this is plus. Now, this force is against x1, so it will come with a minus sign. Yeah. And for M2, this same force, which was a plus for M1, for M2, it will be a minus. No, sorry. Here it was a minus because it was against x1. But this arrow for M2 is in line with x2, so that will be a plus. Now K2 x2 is against x2, so that will come with a minus sign. Okay, so we don't need anything else because this is our equations of motion. Okay, equations of motion. You don't need to write one equation. You have two equations of motion, and that's good enough. They are both independent. Okay. Now this is the same problem, but this time you have the rotational version. Okay, so you have torsional springs here, and you have rigid bodies that are inertias. And this time you have three springs. So instead of looking at this 3D view, which looks confusing as far as the torsional springs are concerned, and the first thing you need to note is that for theta1 and theta2 is equal to 0, the springs are at their free lengths. So which means that the free length is not taken into account. You measure theta1 and theta2 from that free length. So you do not have to mention it explicitly. But let's draw the free body diagrams for the two bodies. I1, let's say this is I1 and this is I2. Okay, I1, I2. There is no translation, so we should not bother ourselves about the masses. Okay. Now here the if I look at it from this angle, then theta1 is in this direction. Okay. And I don't care whether it's clockwise or anti-clockwise because everything else will be now dictated by this theta1. And for I2, theta2 is in this direction. Now, if I look at theta2, or maybe I start with theta1, I1, because this is the support, so theta1 will have a twisting effect on K1, and that effect will be opposite to theta1. So it will be K1 theta1 will be the restoring torque applied by I1 by this K1, by the spring K1. Okay. Actually, there is no. Okay, no, there is another one as well. This K2 will also apply some restoring torque. So again, you have to make some assumption, and if you assume that theta1 is less than theta2, I'm just assuming that because I somehow guess that T2 will have some effect. So T2 may make theta2 greater than theta1, but you can still make the assumption. The opposite assumption is also good enough because you don't know the value. So, but let's stick with theta1 less than theta2. When theta1 is less than theta2, basically I1 will try to trail behind I2. So it will kind of uh, push the spring in this direction, okay? And the restoring torque from K2 will be an opposite of that, okay? Yeah, it will be opposite of that. So it will be K2 times theta2 minus theta1. Remember, I'm assuming theta2 to be greater than theta1. The torque on I2 will be opposite. If this is clockwise, anti-clockwise, this will be clockwise because they must cancel each other. Theta2 minus theta1. And this angle will also twist the spring labeled K3, and the restoring torque will be opposing that. So that will be K3 times theta2. Now you just need to write the moment equations. Moment equations for I1, which is I1 theta1 double dot, and for I2 theta2 double dot, and you know which torques are plus, torques which are in line with theta1 are plus, torques which are against are minus. Similarly, plus, minus, and these are your equations of motion. Okay, T2 is the input. So that is very much similar to this problem. Okay. Now, so you have seen that in these problems, in this one and this example, and in this problem, it is not so easy to keep track of all these internal forces, action reaction pairs, although and you have to eliminate them. So any mistake you make can actually have serious consequences, and that means that just like before, we should be using energy methods. The most popular energy method and the easier one is when you add the kinetic energy to the potential energy, which includes the spring energy, the elastic energy, the gravitational potential energy, and so on. And you just call them Hamiltonian. And if you don't like that name, you can simply call it mechanical energy. And it turns out that any change in that mechanical energy can only come from the work done by non-conservative forces. Non-conservative is important, like friction forces, applied forces by motor, and things like that. It will not include gravitational forces or spring forces. If you want to differentiate them, okay, um, that is the rate form. And if this is complicated, then you can take, instead of this mechanical energy, you can take the Lagrangian, where you subtract potential energy from the kinetic energy, and then you can write the Euler-Lagrange equations. They also give you the differential equations. But we will prefer to use these as much as possible. Only when this doesn't work, we will come to this. So here is a complicated example. We have seen this before as well. You remember in that previous example, this h was 0, and this weight was actually placed on the platform. In this example, it's a bit more complicated. You have this weight which is at a height h, and it falls down and it hits the platform. You assume the platform to be massless for simplicity, and when it hits this platform, it actually compresses spring K1, and if x is less than d, the only restoring force comes from K1. But if it is compressed too much, then at some point spring K, these two springs also get compressed, and they also experience the deflection. Now the deflection in K1 is x directly, yeah, but the deflection in x2, the reflection in K2 is not x, because that starts after d, so that will be x minus d. Yeah, the deflection, because when x is equal to d, there is still no deflection, so x minus d will be 0. Only when x exceeds d do we see any deflection in K2. So we can easily have two cases, yeah, case x less than d, in which this is the only system of interest, okay. These two springs are out of the picture. And when x is greater than d, then all the three springs are part of the system, because they will contribute the restoring force. Okay, so let us try to let us see what is required in this question. The figure shows a representation of a spring system to isolate foundation. This is the foundation, okay. इस फाउंडेशन को इस वेट से बचाने के लिए ये 3 स्प्रिंग्स लगाए गए हैं, ठीक है. So suppose the weight W is dropped from a height h above the platform attached to the center spring. ये height given है, and determine the maximum spring compression and the maximum force transmitted to the foundation. ये springs ही force transmit कर रहे हैं, so we need F max and we need X max. X की maximum value, और जब वो मिल जाएगी उसी से हमें F max is equal to using Hooke's law, we will get the maximum force transmitted to the foundation. So we need to now write down the equations, but instead of writing down the equation, we should use the energy methods, okay? And our purpose is only to write the to find out the maximum spring compression. Now, so we will try to write down the expression for the kinetic energy, for the potential energy, this curly V, and then we will add the two K plus V, and we see, okay, we can ask the question that how much this total kinetic energy and total potential energy change. And that change must be zero because there is no external non-conservative force. Non-conservative forces are zero. Sorry. Non-conservative forces and non-conservative moments are zero. So if you remember this discussion, delta H can only arise from non-conservative work done, that is zero. So we can now focus on delta K and delta V. Now, what is delta K? The change in kinetic energy. Now, it starts from this position at rest. So the kinetic energy there is zero. And even if it is not zero, it has some value. And then if it compresses these springs, this one or all the three, to the maximum level, then it will have to come to a halt because there will be restoring forces, and restoring forces will ultimately balance W, and it will come to a halt, a stop. So when it stops, it will get back the original kinetic energy, which can either be zero or non-zero. So the change will be zero. The change in kinetic energy must be zero. So which means that we can only we should only bother about the potential energy. So we will now write down the let me just draw a sorry, let me draw a white rectangle so that I can hide some of the details, and we focus on the oh sorry we focus on the uh, potential energy, yeah, because we know change in kinetic energy is zero, and we need to find out an expression for the change in potential energy, and that must also be zero. And we first consider the case when x is less than d. X is less than d means that only spring k1 is contributing to the um, kinetic energy. Now, it is half so it will be half k1. Normally you would say x squared, okay? And because it's change in energy, so let's say that the maximum is x max, and the minimum value of x min is zero. Yeah, it has not deflected. So it will be x max squared minus x min squared. This will be the change. And remember, this is the elastic potential energy. Elastic. We also need a term for the gravitational potential energy. Okay, and that is normally we write something like mgy. Yeah, but mg in this case, mg, it's actually that idea was very stupid. That whenever I have this, if I write on top of this, I cannot delete it. Okay, so I have to live with this, and I will delete it in this way. Okay, So instead of mg, I will write w because that is the weight. W is equal to mg. So I'm just writing w. And w times h, of course, plus x. x h के बाद शुरू होता है, ठीक है? And now the question is whether it's plus or minus. So that depends on the reference. So if we take this initial to be our reference, we can take that potential energy to be 0. So the change will now be minus, okay, because it's coming down. So now this is now our equation for x less than d. Now, शो नहीं हो रही? अच्छा, ये क्या नहीं, ये मीटिंग खत्म हो गई है, क्या चक्कर है ये? नहीं नहीं, ये फिर मेरे ख्याल में लाइट चली गई थी, लाइट गई थी ना, और ये मुझे आवाज नहीं आई। हाँ नहीं, क्लास तो शुरू हो गई थी ना, ये बीच में लाइट गई है। मैं ये कह रहा हूँ ये लाइट चली गई और मैंने नोट नहीं किया ना, इसलिए। समझ आ गई ना, क्लास तो शुरू हो गई थी, वरना मैं ऐसी हवा में तो नहीं चल रहा था। अच्छा, आवाज आ रही है आपको लोगों को अभी?
यस सर।
तो ये बताएं, असल में यहाँ पे लाइट चली गई और मैंने बिल्कुल नोट नहीं किया, तो कहाँ पे हम ये डिस्कनेक्ट हुए थे? क्योंकि इस दौरान तो काफी मैं आगे चला गया हूँ।
सर जीरो
काफी
कहीं से
देर
आपकी
से
आवाज ही नहीं आई।
हाँ,
आपकी कहीं से भी आवाज नहीं आई शुरू से ही
नहीं आई।
नहीं, शुरू से तो मैंने कंफर्म किया था ना कि आप को स्क्रीन नजर आ रही है, नहीं नजर आ रही?
नहीं सर, आपकी वो भी आवाज नहीं आई।
नहीं नहीं, वो तो
Sir,
मुझे
first 20 seconds about.
अच्छा, तो आप ये कह रहे हैं कि लाइट बहुत शुरू में चली गई थी?
बिल्कुल शुरू में।
आतिफ, आतिफ साहब, अच्छा 1:45 पे चली गई थी, अच्छा ठीक है। अच्छा नहीं, फिर आप इस तरह करें ना, लाइट जब चली जाए उसके बाद मुझे रिमाइंड किया करें ना, क्योंकि मैं शायद मैंने नोट ही नहीं किया ना। तो ये मसला है। हालांकि यहाँ पे कोई ना कोई इंडिकेशन होती है, लेकिन बस अनफॉर्चुनेटली मैंने नोट नहीं किया। लेट्स try to wind up things. ये आपको नजर आ रही है अभी ये वाली स्लाइड?
यस सर।
अच्छा, मैं इसको फिर ये कह रहा हूँ कि मैं इसको डिटेल में नहीं करूँगा, क्योंकि द एग्जांपल्स आर प्रॉब्लम्स एंड एग्जांपल्स आर मोर इम्पोर्टेंट। ये फिर आप आराम से देख लें। इसमें ये मैंने सिर्फ कोशिश की है कि जो सिंपल हार्मोनिक मोशन है, इट इज बेसिकली a second order differential equation, and you can write it in this alternative form where you apply this derivative with respect to omega nt, because omega nt is dimensionless. And if you apply that operator twice, and because you do need this minus sign, so I first take this 1 omega n squared to the other side, and I put the minus sign in the bracket, and then I call this, I give this a new name, let's say y. That give me one differential equation, and now this derivative applies on that y. So instead of one second order differential equation, I have two first order differential equations. That is, you can do that very easily. The advantage of this is that you have a single ODE in the complex plane. ये x और y को अगर मैं complex plane में देख लूं, so I have a single differential equation, and the the cool thing about this is the derivative is the same as if you are rotating it by 90 degrees. आप x y से start करें किसी भी जगह पे, तो ये देखें ना x y को अगर minus y x से compare करें तो basically it's a rotation of 90 degree counterclockwise, and that is what we can represent by j. अब ये तो खैर आप लोगों ने पहले भी पढ़ा होगा फेजर्स वगैरह में, but you can solve this differential equation with initial conditions and you will have a solution like that. अब ये time की वजह से I don't want to explain this further, but the upshot of this equivalence that the derivative is the same as if you apply this rotation and multiplication by omega n, that is seen here. Let's say this is the solution. You can write it in this way or in this way. There are two alternative forms of writing the solutions. And the actual values of a and theta or a and phi will be determined by the initial conditions. That is something you can do later. But the derivative will have this pattern. The magnitude will be multiplied by omega n because multiplication is there. And the angle will advance by 90 degree. Yeah? Whether you use this form or this form, you will always see this plus pi by 2. And if you do that twice, yeah, derivative twice, omega n will multiply twice, so squared, and pi by 2 will add twice, and that is something which you can see here as well. Okay, this is your x, dx over dt is advancing by 90 degree, and d squared x over dt squared is advancing by 180 degree. So there is something which you can remember. In problem 2.3, you see, apart from the spring, you have been dealing with these problems over and over. So now we will only include the spring. And if you remember the free body diagram, you have this tangential force Ft, which was the internal variable. And then then you had this, and this is your input. So you take the displacement as an input, yeah. And we don't care where this displacement is actually generated, but there is some mechanism which gives you the displacement. And now this spring is under these two displacements. So if I assume x to be less than y or greater than y, it's up to you. If I assume x to be less than y, with respect to y, I can imagine that this end is trailing behind, and that is the same as stretching the spring to the left. So that will give me a restoring force opposing that, and that will be k times y minus x. Remember, y is greater than x, so y minus x. If I had assumed x to be greater than y, then this arrow would change, and this will also change. Okay, this will go with x minus y. It's up to you. So I prefer that one because that is in line with x. So it's x times y minus x. Okay. So I can now write down the, and I will skip the solutions part because solution of differential equations is not part of this course. So I can now write the equation of motion for the translation, and that is mx double dot, which is equal to minus ft because this is against, and plus k times y minus x. This is the first equation. And because there is a moment as well, and ft is the only force which gives you moment, ft times r is the moment, and that is in line with theta, so it will be with a plus sign. And the spring will have no moment because it passes through the center of mass. And I can now write down I theta double dot. But I also know is half mr squared, okay, for a cylinder. And because it rolls without slipping, so I also know that x equals r theta, x dot equals r theta dot, x double dot equals r theta double dot. So which means that theta double dot is x double dot over r. So I can now replace theta double dot with x double dot divided by r. Now this r will cancel out with this r, and that r will cancel out with this r. And now I can now add these two equations because plus minus will cancel out. So on the right hand side I have k minus y, k times y minus x. On the left hand side I have x double dot, and m plus half of m is 3m over 2. And you can then simplify this. Okay, so this was easy. Okay, this example looks more complicated, but the principle is the same. You have two rigid bodies, you have free body diagrams for both x2 and x1 are two displacements, depending on whether you assume x1 to be greater than x2 or x2 to x1 to be less than x2. In this case, k1 is being stretched downwards, so this is the restoring force, and the restoring force for m2 is the opposite. x2, if you assume x2 to be positive, you are stretching k2 downward, so this is the restoring force, and similarly these arrows are for x2 less than x1. So once you have these free body diagrams, because there is no rotation, so you can simply write the equations of motions for m1 x1 double dot and for m2 x2 double dot. Forces for m1 are F, and that is in line with x1 actually in the same direction, so it's plus, and the restoring force of the spring is opposing it, so it's k1 x1 minus x2, and that same k1 x1 minus x2 is with a plus sign because it's in the same direction with x2, and k2 x2 is opposing x2, so that's the minus sign, and you immediately get the equations of motion. Okay, you can leave it like that because it's not the equation but equations, so you can write two equations, that's good enough. Now here, all this looks complicated, but it's actually the exact same problem. The only difference is that instead of translation you have rotation. So you have two free bodies, rigid bodies. I can now depict them like that. One for I1, one for I2, okay? And ये मैं एक कॉल उठा लूँ एक सेकंड. हेलो जी, वालेकुम सलाम. जी 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 जी, कैसे मिजाज है? इस्लामाबाद से लगी है F9 पार्क से. नहीं, पहले वाली G9 CDA जो CDA सेंटर है. जी जी. वो नहीं, वो कह रहा है कि आपका जो है ना पाकिस्तान ओरिजिन कार्ड है और वो नहीं मानता. वो कहता है आप पासपोर्ट नंबर दे दें और उसके बाद वो कहता है कि आप तो रजिस्टर्ड ही नहीं है. हाँ, पीओसी की वजह से वो प्रोसेस आगे नहीं जा रहा. वो नहीं, वो डाला है. जब मैं वो डालता हूँ तो वो कहता है कि आप रजिस्टर्ड नहीं है, वो रिसेट हो जाता है वो उनका सिस्टम. उनका सिस्टम जो है ना, जब मैं पासपोर्ट इंटर करता हूँ ना, तो वो कहता है कि आप रजिस्टर्ड नहीं है, तो वो सिस्टम कंफ्यूज हो जाता है. जी 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 जी, बिल्कुल बिल्कुल, ये मेरा भी इशू है, मेरी वाइफ का भी इशू है. हाँ, बिल्कुल 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 बिल्कुल. तो इशू डोज का नहीं, इशू पीओसी का है कि पीओसी उधर सिस्टम में जो है ना वो उसको वो कंफ्यूज हो जाता है वो सिस्टम. ठीक है, ठीक है, थैंक यू, थैंक यू. ओके, so you have these two free bodies, and of course one of them has an external torque, so I can just label that like that, and it is in the same direction as theta 2, and here you have theta 1, and depending on whether you assume theta 2 to be greater than 1 or less than 1, I just make this assumption. You can now say, okay, the restoring torque will be based on this. So if you assume theta 1 to be less than theta 2, I1 will be trailing, and that means that if I1 is trailing, it will try to stop to trail K2 in its direction, and that K2 times theta 2 minus theta 1 will be opposing that. It will be opposing the moment of theta 1. and for the second body it will be the opposite. Okay, so if this is counterclockwise, this will be clockwise. That's why they cancel each other. And the okay, the force from K1 will also be opposing. Okay, K1 theta 1, and the force from K3 will also be opposing. Yeah, so you have these different torques, torques which are in line with theta 1 will be plus, which are against theta 1 will be minus, and that's how you can write down the moment equation for theta 1 double dot I1. And similarly for theta 2 double dot I2, and torques which are in line with theta 1, theta 2 positive against theta 2 negative, and this is how you write the equations of motion. That was not so difficult. Now here this example looks complicated, but we can before the example we can just recall that we can, instead of writing the differential equations which will involve internal forces, internal moments and cancellation, and it looks very complicated. So why not writing just an expression for the mechanical energy, which is the kinetic energy plus the potential energy, including all the springs, gravitational field and so on. And that mechanical energy can only change by work done by non-conservative forces like friction or motor or any force you apply from the outside world. If you want, you can also write the differential equations. The Lagrangian is the alternative method, which is for more complicated problems, but for our purposes, this will be good enough for most cases. So if we have this problem, let's say we have a spring that is meant to isolate the foundation, this is the foundation, from a weight falling on a platform, and you see that drops from a height, and let's say you take this to be your reference, so the potential energy will be zero there, which means that the potential energy as this weight comes down will be negative. So we are to determine the maximum spring compression and the maximum force transmitted. So because of this D, if there are two cases, one is x is less than D and two is x is greater than D. When x is less than D, this platform and this weight can only interact with the spring K1, okay, because K2 has not started interacting. When x is greater than D, then all the three springs are interacting. So we will take these two cases different, and in the first case, which is x is less than D, I can now write down the change in kinetic energy and the change in potential energy. Change in kinetic energy is zero because it starts from rest, and because we are interested in the maximum spring compression, ये maximum तभी होगा जब ये restoring force इसको balance कर देगा. जिस तरह कैपेसिटर में आप चार्ज करते हैं ना, तो वो चार्जिंग रुक तब जाती है जब ये internal voltage external को balance out करता है. So this we will call it the maximum spring compression only because the restoring force will balance that weight. तो इसका मतलब ये है कि initially भी rest पे है और finally भी it must come to a rest and the kinetic energy must not change. The potential energy change is something we need to now calculate. तो potential energy change क्या है? वो है half तो spring K1, so K1 x squared, okay, and because we need maximum, so I just put a label x max. और चूंकि change है, so basically we are also doing half K1 x min, और वो min हमें पता है कि वो zero है, minimum value x की zero है, so we can write that down to be zero. So this automatically gives us the maximum change. Similarly, we need an expression for the gravitational potential energy. Gravitational potential energy में you multiply the weight by the change in height. Change in height क्या है? It first drops by this height h, and then it drops by height x, and because they are both below the reference, so I'll put a minus sign there. Yeah. And now this must equal 0 because ये भी 0 है, ये भी 0 है, the total must be 0. Total must be 0 because there is no non-conservative force. Friction force यहाँ पे नहीं है, कोई और force नहीं है external. Now if you want to plug all these different values, these values, this can get complicated. So what I have done is that you have to look carefully when you read these slides at home. I have tried to divide like quantities by like quantities. So if you divide h by d, height by d, you get a non-dimensional number. If you divide k2 by k1, you get a non-dimensional number. Similarly, if you divide x max by d, you get a non-dimensional number. And if you divide the weight by k1d, remember k1d, k times d will have the units of force because restoring force. So that will also be non-dimensional. And which means that if I now divide both sides by k1d squared, and I recognize these patterns, I can easily say that for this condition when x is less than d, in other words, x over d is less than 1 and x over d is x prime, actually x max over d. So for this condition, w prime will have this value. And the same applies to the other condition. When I say that, okay, x is greater than d, now I have all the three springs intact. So k1 and then k2 or k2 का सिर्फ ये है कि instead of x I will have to take x max minus d squared, और वो सारी चीजें अगर मैं ये नॉन डायमेंशनलेशन में इंक्लूड कर दूं, so I will have the other expression. So we now have a dual expression for w prime depending on whether x is less than d or greater than d. At the boundary, you can verify that the value is 1/12. So w prime की जो value है, ये नॉन डायमेंशनल w प्राइम की, ये 1/12 है. अब हमारे पास चूंकि दो पार्ट्स है, पार्ट ए और पार्ट बी, it turns out that this 64 Newton, when you normalize this turns out to be less than 1/12, and this 256, when you normalize, this turns out to be greater than 1/12. So basically ये जो दो parts हैं, they correspond to these two conditions. Yeah, and you can solve, because ultimately तो आपका maximum compression चाहिए, so you can solve this equation. It turns out to be a quadratic, or you can solve this quadratic. और quadratic के जो कि दो solution होते हैं, आपने वही solution लेना है जो उस inequality को satisfy करता है. So it's end पे आपके पास आराम से maximum compression आ जाएगा. And when you find the maximum compression, the maximum force is easy. For the first case, it's simply k1 times x max, because that's the only spring. But for the second case, it's k1 times max plus जो k2 यहाँ पे जो maximum डिफ्लेक्शन है, और वो है x max minus d. बाकी आप हमने बुक में देख लें. This is another example which we can solve by the energy method. And remember, this is the free length, and typically we take this free length to be our reference. तो यहाँ पे potential energy 0 है. And we also know that this deflection delta st is because of the weight. So when mg drops by an amount x, it should balance out a restoring force of k times the static deflection. So this is what we will remember. And if you want to write the energy, the kinetic energy is half m x dot squared. इसमें डेल्टा एस टी इसलिए नहीं होगा कि वो स्टैटिक डिफ्लेक्शन है, उसका डॉट 0 होता है. एंड द पोटेंशियल एनर्जी इज हाफ के एक्स प्लस द स्टैटिक डिफ्लेक्शन स्क्वायर्ड. ठीक है, ये एल वाला इसलिए मैंने नहीं किया कि वहां पे पोटेंशियल एनर्जी 0 है, तो हम काउंट नहीं कर रहे. प्लस एम जी एक्स, और ये प्लस नहीं होगा, माइनस होगा, क्योंकि रेफरेंस उधर है, तो जब नीचे आएगा तो एनर्जी पोटेंशियल एनर्जी नेगेटिव में जाएगी. So I can even expand this. It will be half kx squared plus half k delta st squared plus twice or half cancel हो जाएगा. So I'm left with kx delta st minus mgx, but I know minus अच्छा ये mgx नहीं है, सॉरी ये mg है, ठीक है, because force और ये restoring force will equal the force of gravity. ये mgx से मैंने पिछले क्लास में भी ये मिस्टेक किया था, mgx तो मोमेंट होगा ना, so you cannot equate a force to a moment. So because x is common in these two and mg is equal to k times delta x, so these two terms cancel out and you are simply left with v is equal to half kx squared plus half delta st squared. And now the total energy H is k plus v, which is half mx dot squared plus half kx squared plus half delta st squared. And I can now simply differentiate this, and this derivative must give me 0 because there is no external force, no external work done. Remember, yeah, non-conservative. We don't have any non-conservative force. So H dot, you differentiate this half or 2, the power rule wala 2 cancel ho jayega, so it's mx dot and then x double dot plus kx and x dot, और ये इसका डेरिवेटिव 0 है क्योंकि स्टैटिक डिफ्लेक्शन है. If this is 0, I can take x dot common, divide both sides, and I'm left with mx double dot plus kx is equal to 0, and I got my equation. ये already आपको पता था, but this is just to show the power of energy method. Same goes here. In this, again, we are told that at x is equal to 0, we have equilibrium position, so वहाँ पे हम potential energy 0 मान लेंगे, ठीक है? And neglect the mass of the pulley and assume the cable is inextensible. दो चीजें हैं. पुली का मास नहीं है, इसका मतलब यह है कि काइनेटिक एनर्जी जो पुली की वजह से वो 0 हो जाएगी. द केबल इज इनएक्सटेंसिबल का मतलब यह है कि ये केबल अगर एक्सटेंसिबल नहीं है तो वहां पे कोई स्प्रिंग नहीं होगा, तो उसकी पोटेंशियल एनर्जी भी 0 हो जाएगी. स्प्रिंगीनेस नहीं है. सो इसका मतलब यह है कि दिस यू कैन थिंक ऑफ इट एज अ रिजिड बॉडी, और फिर इसका मतलब यह है कि जो एनर्जी बनेगी वो सिर्फ m1 और m2 की वजह से बनेगी और k की वजह से बनेगी. सो लेट्स राइट डाउन द काइनेटिक एनर्जी फर्स्ट. एंड बिकॉज आपको पता है ना कि जब आपके पास स्प्रिंग होता है उसके दो एंड्स डिफरेंट हो सकते हैं डिस्प्लेसमेंट वाइज, लेकिन रिजिड बॉडी में अब ये m1 और m2 चूंकि दे आर कनेक्टेड बाय रिजिड बॉडी, सो m1 m2 एंड दिस रिजिड बॉडी दे विल ऑल हैव द सेम डिस्प्लेसमेंट. तो यही x इधर भी एप्लीकेबल है, ठीक है, कोई डिफरेंट x नहीं होगा ये बिकॉज ऑफ द रिजिड बॉडी. सो दैट मीन्स दैट आई विल हैव हाफ x dot squared and x dot belongs to m1 as well as m2, so I add the two. And potential energy एक तो आ जाएगा इसका हाफ के एक्स स्क्वायर्ड, और x में आपके पास वो डिफ्लेक्शन, वो जो स्टैटिक डिफ्लेक्शन है वो भी आ जाएगी. सो हाफ के प्लस के टाइम्स x प्लस डेल्टा स्क्वायर्ड प्लस m1 moves only horizontally, so इसका कोई वो जो पोटेंशियल एनर्जी नहीं है, लेकिन m2 goes vertically, उसका होगा. So that is m2 g x. m2 जब नीचे आता है तो because potential energy x is equal to 0 पे 0 है, so if something comes below, the potential energy will decrease. So that's why we have a minus sign. And we also know that m2 times g must equal k times the static deflection. That is something we have to remember. So if I now expand this, it will be half kx squared plus half k delta squared plus twice half cancel k x delta minus mg2x. X common है, k delta must equal m2g, so that will also cancel out, and our total energy H is k plus potential energy. You just add these two, half m1 plus m2 squared x dot squared plus half k x squared plus half k delta squared. And if I now take the derivative, so it will be m1 plus m2 x dot x double dot plus kx x dot, और इसका derivative 0 है, set to 0, cancel out x dot on both sides, and now you have m1 plus m2 x double dot plus kx equals 0. So that was also easy. Now, so we basically so far have two methods. Okay, we have the method of equations of motion from free body diagrams, which requires Newton laws, and the other method is the energy method. But in both cases, we write the equations of motions. Sometimes, if in particular, if you're dealing with simple harmonic motion, and if all you have to do is to find the natural frequency or time period, then it's not a good idea to waste time by writing the equations of motion, even by the energy method. Even that is a waste of time. So what you can do is this is what Rayleigh method does. It starts with the observation that the energy conservation for simple harmonic motion follows a pattern that when the kinetic energy is maximum, the potential energy is minimum because they exchange. So if one goes high, the other must go low. And if kinetic energy is a minimum, the potential energy must be a maximum. And kinetic energy, the minimum kinetic energy is 0, yeah, because typically we assume rest position. Even if it is not rest, we take that out of the equation to cancel out. So if I set this to 0, it turns out that the maximum kinetic energy is simply the difference between the maximum potential energy and the minimum potential energy. हम जब ये लिखेंगे, this will give us the natural frequency. So we are not going to write down the differential equations. So this is basically a practice for that principle. If I start with this picture and I want to apply the Rayleigh's method to determine the natural frequency without writing down the differential equations. So अब mass moment of inertia यहाँ पे क्या है? I है. Translational inertia is m, which is mass, and assume that this cylinder rolls without slipping. अब इसका भी हमें मतलब पता है, but first let's write down the kinetic energy. अब kinetic energy यहाँ पे क्या है? Half m x dot squared plus half I omega squared. And we would like both to be written down in either omega or omega x dot square x dot, but we also know that x dot equals r omega if it is without slipping. So omega must be x dot divided by r. So omega squared must be equal to x dot squared divided by r squared, which means that I can now take x dot square common and half s common. So I'll be left with m plus I divided by r squared. Okay. So for simplicity, I can just write IE, and later on I will replace this with this expression. So writing IE initially will be easier for me. Potential energy is, we start with the spring, so it's half k x squared, and again there will be a static deflection delta. Now that static deflection can be seen that it comes basically from the weight mg. Okay. Now it's actually the component of mg, yeah, ये वाला component, और ये वाला component mg का है mg sin of alpha, ठीक है. And we also need to write down the gravitational potential energy. That is, अगर हमने x is equal to 0 को रेफरेंस मान लिया, पोटेंशियल एनर्जी वहां पे 0 है, सो जो x का जो y कंपोनेंट है, ये हॉरिजॉन्टल वर्टिकल कंपोनेंट, वो है x sin of alpha, and we need a minus sign because the potential energy will decrease when you come down from that reference, or ref wet mg है, so mg times that vertical distance minus sign because the reference of नीचे आ रहे हैं, and if we now expand this, it's half kx squared plus half k delta squared plus twice half cancel kx delta minus mg x sine of alpha. And you know that this, if I take this x out, if I take this x out, these two cancel out, okay? So I am left with the same basically scenario. But this time I'm not going to write that h dot equals 0 thing, because that will be like writing down the differential equation. I want to find out the maximum and minimum values. So let's write the maximum value of the potential energy, that is half k x max squared plus half k delta squared. Delta is a constant, तो उसमें max का चक्कर नहीं है. What is the minimum potential energy? Again half k delta squared को कुछ नहीं होगा, x की minimum value 0 है, तो वो 0 मैंने कर दी, and k max is of course यही expression half IE और x dot max squared. अब यहाँ पे x dot max हमें मसला कर रहा है, and for this I can now remind you the very first slide कि simple harmonic motion की एक beauty ये है कि even if you don't remember these expressions, the amplitude or maximum value of x is related to the maximum value of x dot by omega n. आप सिर्फ क्या कर ले, x max अगर आपको पता है, multiply that by omega n and you will get x max dot. So derivative, the maximum of the derivative is the maximum times the natural frequency. We will just use that result here, and that is half IE expression आप बाद में कर लें, x max is omega n times x max dot is omega n times x max, omega n भी squared हो जाएगा, ये भी squared हो जाएगा. Now you plug this value and this value in the Rayleigh's method. Rayleigh's method क्या है कि k max, which is this value, equals v max, which is this value, minus v min, which is this value. ये तीन वैल्यू इस इक्वेशन में प्लग करें, the only unknown is omega n, क्योंकि x max दोनों साइड पे कैंसिल हो जाएगा, और ये जो हाफ k डेल्टा स्क्वायर्ड है, ये भी डिफरेंस की वजह से भी कैंसिल हो जाएगा. x max इस साइड पे भी है, x साइड पे भी है. the only unknown in this algebraic equation will be x max. So we are done with this now. If you have any questions, we can still entertain those questions. Okay. Okay, let's stop this recording first.